Welcome to The Explainer. All right, today we are going to talk about leveling up your Python code. Taking those scripts that, yeah, they work, but they're not exactly what you'd call professional. We're going to turn them into applications that are seriously fast, super resilient, and actually built to last. So if you've ever written any Python, you know this feeling, right? You start with this neat little script and it works perfectly. But then you add a new feature, you throw a bigger data set at it, and suddenly it just slows to a crawl, it crashes if you look at it wrong, and before you know it, it's this tangled mess of code that you're actually kind of scared to even touch. Well, the good news is there is a clear path out of that mess. So today what we're going to do is build a kind of mental toolkit. We're going to stock it with 4 essential power tools that solve these exact problems. We'll figure out how to make our code faster, safer, way better at handling data, and just easier to understand. And we're going to start with the one everyone always wants, speed. Okay, first up, concurrency. This is our answer to the need for speed. At its core, concurrency is really just a fancy word for structuring our programs so it can juggle multiple tasks at once. It's about not getting stuck waiting for one thing to finish before starting the next. Now, before we go any further, we have to get this one thing straight. Concurrency is not the same as parallelism. Think of it like this. Concurrency is like a chef juggling multiple recipes in one kitchen, chopping veggies for one while something else is simmering. Parallelism is like having multiple chefs, each in their own kitchen, working at the exact same time. Now, here's the kicker for Python. It has this thing called the global interpreter lock, the GIL. You can think of it as a rule that only allows one chef, one thread, to use the main kitchen equipment at a time. This means for heavy-duty cooking or CPU-bound work, you don't get true parallelism with threads. And honestly, that one single fact changes everything about how we write fast Python code. So what this all means is that the single most important decision you have to make is figuring out why your code is slow. What's the bottleneck? Are you spending most of your time just waiting? Waiting for a network request to come back or waiting for a file to be read from a disk? That's called I/O bound. Or is your code actually sweating, doing some heavy number crunching and complex math? That's CPU bound. And trust me, the tool you pick to solve the problem is completely different for each one. And this is where it all comes together in a really simple choice. If your code is I/O bound, all that waiting around for networks and files, then threads or async I/O are your best friends. They are fantastic at waiting efficiently. But if you're CPU bound, if you're really pushing that processor, you have to use processes. This is the only way to completely sidestep that GIL we talked about and actually use all of your computer's CPU cores at once. Okay, let's look at a real-world example. Say you need to fetch a bunch of web pages. Instead of doing them one by one by one, we can use a thread pool executor. It's actually pretty simple. You just tell it, hey, I want 5 worker threads. And then you use this map function to hand over your fetch function and your list of URLs. The executor handles the rest, firing off those requests concurrently. So while one thread is just sitting there, waiting for a slow server, another one is already off and running, fetching a different page. For anything involving a lot of waiting, this is an absolute game changer. It's a huge speed up. All right, so our code is fast, but what happens when things go wrong? Let's talk about our second power tool, exceptions. This is all about tackling that all too common problem of scripts that just fall over and die at the first sign of trouble. See, robust applications don't just hope for the best, they plan for failure and handle it with grace. The heart of handling errors in Python is the try/except block. You can think of it as your safety net. You put the code that might fail, your risky code, inside the try block. If something goes wrong, Python jumps immediately to the except block where you handle the problem. Now, there's a cool little part you might not use often, the else block. That code only runs if the try block succeeded with no errors at all. And then there's finally. This one is your guarantee. The code in the finally block will run no matter what, whether there was an error or not. It's perfect for cleanup tasks like closing a file. And this brings us to a really important mindset. The goal here is not just to catch errors to stop your program from crashing. It's about handling them gracefully. You never want to just catch an error and then do nothing. That's called swallowing an error, and it's a terrible idea. Instead, you should log what happened, maybe try the operation again, or at least give the user a helpful message. You're building code that expects the unexpected and actually has a plan for what to do. Okay, here's a pro move that will make your debugging sessions so much easier. Sometimes you'll catch a specific error, but you want to raise a more general error to the rest of your program. If you just raise a new one, you lose all the information from the original. But if you use raise runtime error from exec, you're chaining them together. This preserves the original error's traceback. And let me tell you, this is an absolute lifesaver. Your error logs will now tell you the entire story of what went wrong from the very beginning. It's amazing for finding the root cause of a bug. All right, so our code is now fast and it doesn't crash at the drop of a hat. Awesome. Now let's talk about our third tool, I/O, or input-output. This is all about how our application talks to the outside world, how it reads files, writes data, and does it all without, eating up every last bit of memory on your machine. When it comes to reading files, you basically have two choices. The simple way is to just read the whole thing into memory at once. And look, for a tiny config file, that's totally fine. But if you try that with a gigabyte-sized log file, your application is going to crash. It's a recipe for disaster. The professional way to handle large files is to stream them. You read the file one line at a time, process it, and then discard it. This way, you use a tiny, constant amount of memory, no matter how huge the file is. Now, I'm going to give you a piece of advice that will save you so much pain later on. Ready? Always, and I mean always, specify the file encoding. If you just open a file without it, Python has to guess the encoding, and its guess depends on the operating system. This is how you end up with code that works perfectly on your machine, but then completely crashes and burns when you deploy it to a server. Just adding that little encoding equals UTF-8 argument makes your code predictable, portable, and saves you from hours of debugging really weird errors. Okay, on to our fourth and final power tool. So our code is fast, it's resilient, and it's memory efficient. That's great. But can anyone else understand it? Can you understand it 6 months from now? This is where typing comes in. It's all about adding clarity and creating a contract for your code, making it so much easier to maintain and way less buggy. It's a gift to your future self and to anyone else who has to work with your code. So take a look at this function here, def get user ID. We're left with so many questions, right? What even is user ID? Is it a number, a string? And what does the function give me back? A dictionary? A custom object? I have no idea. I have to guess or go read the source code. And this kind of ambiguity, it's where bugs love to hide. But now, check out the after version. See the difference? With type hints, the function's contract is crystal clear. It says, hey, user ID has to be an integer. And it says, I will return an optional user. That tells us it's either going to give us back a user object, or if it can't find one, it'll return none. And the best part, it's not just for us humans. Tools like MyPy can now read this and actually find bugs in your code for you before you even hit run. And this gets even cooler with something called generics. This lets you write code that is both super flexible and type safe. For example, you could write a generic repository class that's designed to store, well, anything. But then when you actually go to use it, you can tell it what it's for, like in-memory repo for user. By doing that, you're telling the type checker, hey, this specific repository should only ever hold user objects. It's fantastic. You get reusable code without giving up on safety. Okay, so we've looked at all 4 tools in isolation. Now for the fun part. Let's put it all together. Theory is one thing, but let's see how these concepts actually work in harmony to build a real, robust data processing pipeline. So, step 1, we hit it with concurrency to fix the speed problem. Let's say we have a bunch of rows of data, and for each one, we need to call a slow external API. Instead of doing it one by one, we use our thread pool executor to fire off all of those enriched jobs at once. We're immediately tackling the biggest performance bottleneck head on. Next up, we make it resilient using exceptions. As each one of those concurrent jobs finishes, we wrap the call to get its result in a try/except block. Why? Because what if just one of those API calls fails? Without this, the whole program would crash. But with it, we can catch the error for that single row, log it, and just keep on processing all the others that worked. The application doesn't die. And you see how this all starts with a clean foundation using our other 2 tools? The function that reads the data, read rows, uses type hints. It's perfectly clear. It takes a string and returns a list. No guesswork. And it uses proper I/O handling with the with statement, so we know files are being managed correctly. This solid, predictable base is what allows us to build the more complicated concurrent parts on top of it. So here it is, your whole toolkit boiled down to a simple checklist. When you look at your code, just ask yourself these 4 questions. Is it slow? Reach for your concurrency tools. Could it fail? You need to plan for that with exceptions. Is it touching files or the network? Get your I/O handling right. And finally, is it confusing or hard to follow? That's your cue to add types for clarity. So there you have it. That's the blueprint for taking your scripts from brittle to robust. So now I have a question for you. Think about a piece of code you're working on right now. Which one of these tools, just one, could you use tomorrow to make it just a little bit better, a little faster, a little safer? Because that's how it starts. That's the first step to writing code that is truly built to last.